Hello, and welcome to the 6th episode of the Software Carpentry lecture on the Unix shell. This short episode will show you how to find things in files and how to find files themselves. We're looking at how to interact with a computer using a command line shell. Listening to how people talk about search, you can often guess their age. Just as young people use Google as a verb, crusty old Unix programmers use the word grep. Grep is a contraction of global, regular expression print, which was a common sequence of operations in early Unix text editors. What the grep program does is find and print lines in files that match a pattern. Here's the file we'll use for our examples. It contains 3 computer haikus taken from a competition that Salon magazine ran in 1998. Let's run the command grep not haiku.txt. Here, not is the pattern we're searching for. It's a pretty simple pattern. Every alphanumeric character matches against itself. After the pattern comes the name or names of the files we're searching in. As you can see, the output is the 3 lines in the file that contains the letters N-O-T. Let's try a different pattern, day. This time, the output is lines containing the words yesterday and today, which both have the letters D-A-Y. If we give grep the -w flag, it restricts matches to word boundaries, so that only lines with the word day will be printed, not lines with today or daytime. In this case, there aren't any, so grep's output is empty. Another useful option is -n, which numbers the lines that match. Here, we can see that lines 5, 9, and 10 in the file contain the word it, or a word that contains it. As with other Unix commands, we can combine flags to get only whole word matches with line numbers. Here's another example. -i makes matching case insensitive, while -v inverts the match so that it only prints lines that don't match the pattern. Grep has lots and lots of options. To find out what they are, we can type man grep. Man is the Unix manual command. It prints a description of a command and its options, and, if you're lucky, provides a few examples of how to use it. Grep's real power doesn't come from its options, though. It comes from the fact that its patterns can be regular expressions. That's what the RE in grep stands for. Regular expressions are complex enough that we've devoted an entire lecture to them. If you want to do complex searches, please take a few minutes to watch its first few episodes. One caution. Grep's regular expressions use a slightly different syntax than what's used in most programming languages. However, the basic ideas and rules are exactly the same. While grep finds lines in files, the find command finds files themselves. Again, it has a lot of options, too many to cover here. To show how its basic features work, we'll use this directory tree. Under Vlad's home directory is one file, notes.txt, and 3 subdirectories. Thesis, which is sadly empty, data, which contains 2 files, first.txt and second.txt, and a tools directory that contains the program's format and stats, and an empty subdirectory called old. Here's a textual representation of that same tree created using the Unix tree command. As with ls-f, trailing slashes show directories, and trailing stars show files we could run as programs. For our first command, let's run find.-type d. Here, dot is the root directory of our search. Find will only look in it and the things it contains. -type d means things that are directories. Sure enough, find's output is the names of the 5 directories in our little tree, including dot, the current working directory. If we change -type d to -type f, we get a listing of all the files instead. Find automatically goes into subdirectories, their subdirectories, and so on to find everything that matches the pattern we've given it. If we don't want to go that deep, we can use -max depth to restrict the depth of search. Here, -max depth 1 tells find to only look at this level, so the only file it finds is ./notes.txt. The opposite of -max depth is -min depth, which tells find to only report things that are at or below a certain depth. -min depth 2 therefore finds all the files that are 2 or more levels below us. And here's another option, -empty. This restricts matching to empty files and directories, of which we have 2. We can search by permissions too. Here, for example, we can use -perm -u equals x to find both files and directories for which the user has X permission. Combine this with -type F to exclude directories, and voila, a list of runnable program files. Let's try matching by name with find.-name star.txt. We expect it to find all the text files, but it only prints out /notes.txt. What's gone wrong? Well, if you recall, the shell expands wildcard characters like star before commands run. Since star.txt in the current directory expands to notes.txt, the command we actually ran was find.-name notes.txt. Find did what we asked. We just asked for the wrong thing. Let's try again, but this time we'll put star.txt in single quotes to prevent the shell from expanding the star wildcard. This way, find actually gets the pattern, not the expanded file name notes.txt. Sure enough, this time the output is the names of all 3 text files. As we said in previous episodes, the command line's power lies in combining tools. We've seen how to do that with pipes. Let's look at another technique. As we just saw, find.-name star.txt in quotes gives us a list of all text files in or below the current directory. Here's how to combine that with wc-l to count the lines in all those files. The trick here is to put the find command inside back quotes. This tells the shell to run find and then replace what's in the back quotes with the command's output. This is exactly what the shell does when it expands star, question mark, and other built-in wildcards, but more flexible, since we can use any command we want as our own wildcard. So, when the shell executes this line, the first thing it does is run the command that's inside the back quotes. Its output is the 3 file names datafirst.txt, datasecond.txt, and notes.txt. The shell then replaces the back quotes with that output to construct the command wc-l datafirst.txt, datasecond.txt, and notes.txt. And as you can see, that does what we originally wanted. It's very common to use find and grep together. The first finds files that match a pattern. The second looks for lines inside those files. Here, for example, we can find PDB files that contain iron atoms by looking for the string Fe in all the PDB files below the current directory. If you've forgotten your high school chemistry, Fe is the atomic symbol for iron. So far, we have focused exclusively on finding things in text files. What if your data isn't text? What if we have images, databases, spreadsheets, or some other format? There are basically 3 options. The first is to extend tools like grep to handle those formats. This hasn't happened and probably won't because there are too many formats to support. The second option is to convert the data to text or extract the texty bits from the data. This is probably the most common approach since it only requires people to build one tool per data format to extract information. On the positive side, this makes simple things easy to do. On the negative side, complex things are usually impossible. For example, it's easy enough to write a program that will extract X and Y dimensions from image files for grep to play with. But how would you write something to find values in a spreadsheet whose cells contain formulas? The third choice is to recognize that the shell and text processing have their limits, and to use a programming language such as Python instead. When the time comes to do this, don't be too hard on the shell. Many programming languages, Python included, have borrowed a lot of ideas from it, and imitation is also the sincerest form of praise.